Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will explore and understand UNet, which is an image segmentation model. So let's get started. So first of all, what is image segmentation, right? So image segmentation is a task in computer vision where our goal is to partition an image into distinct region or segments that corresponding to different object or our area of interest, right? So let's understand it simply. So first of all, whenever you are dealing with any image, right? So there are three tasks can be possible. So first, you can check whether your desired object is inside the image or not. So it can be treated as a classification task, right? So if you see this image, so we can ask, is this a dog? So you can say yes or no by training a classification model. And second, you can ask where is the dog, right? So there is, you can predict this kind of bounding boxes and tell here is the dog, right? And third level is you can get which pixel is belong to which class, right? So if you see this red pixel are belonging to a dog class, right? And this blue are from cat and rest are basically a background or it is not our area of interest, right? So this is the segmentation task. So now let's move to the UNet, which is a very powerful image segmentation model. So yeah, so UNet was introduced in 2015, right? And it is fully convolutional neural network and it primarily designed for biomedical image segmentation. So the image segmentation is very useful in medical imaging and in the autonomous vehicle as well, right? So let's see the basic architecture of UNet. So UNet, so let me show you the diagram first so you can get better idea. So if you see this, this is the whole architecture of the UNet, and if you see it's look like a U shape, right? So that's why it is called as a UNet, right? So let's understand it in the detail. So at the first point, if you divide this U in two parts, okay, so the leftmost will be called as an encoder, and this is you can consider as a decoder or expansion block, and this is your encoder, right? So as we know, it is fully convolutional neural network, right? So it will contain a convolutional block, max pooling, and ReLU activation, right? So let's first understand encoder. Okay, so encoder is nothing but a series of convolution and max pooling layer to downsample the image and capturing the higher level context at each step, right? So if you see, this is one block of UNet, and this blue arrow, if you see this diagram, okay, this blue arrow means 3 cross 3 convolution followed by the ReLU, and here also we will apply 3 cross 3 convolution. 3 cross 3 is basically a kernel size and ReLU is the activation function. After we will apply a max pooling, right, with 2 cross 2 kernel size, and it will reduce the size by half, and then we will apply again convolution ReLU and max pooling and so on till here, right? So if you see, each convolution don't have any padding here, right? Let me show you in the paper here. Okay, if you go to the architecture, they had mentioned that it consists of the repeated application of 3 cross 3 convolution with unpadded, which is unpadded convolution. So we are not using any padding, so in result we will get a lower size output, right? So if you see, our input is 572 cross 572, right? But after applying this convolutional operation, we receive 570 cross 570. So of course, as we are not applying any padding here, right? So it will reduce the dimension. And after 2 convolution, we are applying max pooling, so it will be reduced by divided by 2 basically. From 568, we will go 284. And these are the actually channels which we will use, right? So from 64, we will convert into 128 channels, then 256 channel, and so on. So these are basically height and width, or you can say spatial dimension, right? At the end, we will have this bottleneck feature. You can see 1024 channels, right? So after that, till now, we have all information about the image, okay? Or you can say one embedding related to the image. Then from here, we will start to upgrade, or you can say expand the image till here. So here we will use up convolution block, which will increase the image size, right? And these are the respective number of channel which we will use in our implementation, and these are will be height and width. Okay, so same we will use up convolution, and this blue block is basically nothing but a convolution with 3x3 kernel and the ReLU activation function. Okay, and this is called as a copy and crop. So if you see this, you can consider it as a skip connection as well, right? So from here we are passing the information to directly with the decoder block, or you can say expansion block, right? So till here we have all nitty-gritty detail of the image, right? And here we have higher level information of the image. So when we are expanding, we are using this higher level information as well here. Okay, and at the end what we are predicting, we will predict a 2-channel output. Okay, so it will be 388 cross 388. I will explain why it is different 572 and here 388. Okay, so at the end we will get the output of 2 channel. So it will be 388 cross 388 cross 2. Why we here 2? So let's understand, we have only one class basically to segment, right? So in that case, if you consider like only we need to classify or segment a dog. Okay, so there will be 2 class inbuilt. First will be a dog and second will be a background, right? Because we need to also classify the pixel into is it a dog or background, right? So in 388 cross 388 cross 2, the first channel, let's say, will have the probability of each pixel belongs to a background, and second channel will consist a probability it's belong to our desired object, or let's say dog, right? So that's why we are using a 2. If you have 2 objects to detect, then it will be a 3, right? Now let's come to here. So if you see, if you recall the ResNet paper which we had implemented, right? In that we also use this kind of skip connection. But in the skip connection, we had seen we need a same size of output as well here. So if you are providing a skip connection or concatenating this output to here, this also should be this one and this one should be same, right? Let's say here we have 280 cross 280, but here we have 200 cross 200. So we cannot concatenate this output here, right? Because the height and width are not same. So what we are doing, we will centrally crop this image basically. So from 280, we will crop the 200 pixel from the center. So it is also explained here, right? It is copy and crop. When we will implement, you will get the better idea what we are doing. So from this 280 cross 280 image, we will crop 200 cross 200, and then we will concatenate with the output of this decoder block, right? So this is, we are passing the information of the higher level information to this decoder. Same from here to here, right? So this is about the architecture of the UNet. So let's see. So here I also mentioned like what is the difference between the output shape, right? So once you understand the architecture here, how we can provide this higher level information and concatenate with different channel, right? We are basically cropping that particular part from the center. Now you can think how we can train, because let's say in image segmentation, we have segmentation mask of same size, right? According to the input image, let's say 572 cross 572. But our output is 388 cross 388. So what we are doing at the loss calculation, we are also basically cropping a center part of this image. So 572 cross 572, we will crop from center 388 cross 388 pixel, and we will provide this mask and calculate the loss, right? So here I mentioned the same thing. So as we are not using any kind of padding, right? So there would be output mismatch would be there. So what we are doing, we are cropping the ground truth label as well from the center into 388 to 388, which will enable a pixel level comparison, right? And we can calculate the loss on top of that. So it will be like a cross entropy loss itself, right? Because we need to check whether it is what is the probability and it is belong to class or not. That's why it requires the data augmentation very well, because you are missing some information, right, from here to here, and it will focus on the center part of the image. So you need to apply multiple data augmentation technique to get a proper or you can say to teach the model in a better way to all the objects, right? And there are multiple implementations as well of the UNet where the input and output are the same size. Okay, so you can use the different input and same size of output you can receive here, but we are actually currently looking into the paper, so we will stick to this architecture and we will implement this architecture here. Okay, so yeah, this is about the architecture of the UNet. And let's say what is the advantage of UNet, right? So as we seen, right, basically UNet was designed for biomedical image segmentation, right? So if you take any healthcare application, it contains a very less amount of data, right? And the UNet works very well with limited data. So I had written here the biomedical data often limited, making data efficiency essential, right? So UNet is designed to work with a smaller data set very well. So it is working very well with the small amount of data as well. And the second thing, as we are using skip connection, this part, right? So it allows a model to learn higher level and lower level feature as well, very well, right? So it is a very accurate while predicting something. Okay, so these are the two major advantage of the UNet architecture, right? So let's implement it, and so you can get better idea how it is basically work, right? So let's start. So first of all, let's say class. Let me import the library first. Okay, so we are implementing it using a torch. Let's say import torch, import torch dot nn as nn. Okay, so let's say class. Okay, so let me slightly make it bigger, right? So it will be visible. Okay, so class will be UNet nn dot module. Let's say define init. It will self. First we require in channels. Let's provide the argument default 1. Let's say we are dealing with the grayscale images. Okay, and out channels is equal to 2. So basically let's say we have one class to classify, second will be our background, right? So there are two out channels. Let's call the super UNet self. Let's call init. Okay, so now first of all we need to create the encoder, right? So this part let's create. So for this part we had seen here. Okay, let me go to the network architecture. So if you see here, they had mentioned very well, right? So the contracting path is basically an encoder, which we had understand, right? So it consists of repeated application of two 3x3 convolution block, unpaired convolution basically, and each followed by the rectifier linear unit. The ReLU is the activation function. After that, we will apply a 2x2 max pooling with stride 2 for the downsampling, right? So now let's implement that. Okay, so first of all, let's build, I would say, that convolution block, right? So let's say def convolution block. It will receive in channels and out channels, right? So now let's say nn dot sequential. Let's see sequential block here. Okay, first will be convolution con 2d in channels, out channels, and kernel size will be 3, right? And we are not using any kind of padding here. Okay, so now let's say ReLU nn dot ReLU. Let's provide in place is equal to true. Then again the convolution block will require, right, convolution 2d. So basically now for this convolution, this out channel will be as an in channel, right? And the output also will be the output channel, and kernel size will be 3x3, right? And same we need to apply a ReLU. So this is our convolution block. So if you see here, we had written this part, okay, these two blocks basically, these two lines. So if you see from this convolution to this convolution, we are not changing the number of channels. So same we are writing here, the out channels would be same, right? Here we are converting in channels into out channels. Then the next convolution block will contain a same out channels, right? Now let's build the encoder, okay? So let's say self dot enc1. So now we will implement this part, okay? So it is nothing but one convolution block, right? So let's say self dot convolution block. It will require the in channels, okay? And if you see, the out channel would be 64 here, right? So let's write 64. So this is our first part. Now we need to apply a max pooling, right? So it is 2 cross 2 max pooling basically. So and 2 cross 2 max pooling, and we let me write here, then it will be self dot. So we can do one thing as well. We can apply max pooling at the forward method as well. So let's define here only encoder blocks, right? These two blocks only, this part. So let's say self dot enc2 self dot con block, and now it will receive 64. And now, so if you see, we are just increasing channels into 2, right? 64, then 128, then 256, then 512, and then 1024. So let's write here 128. Same thing here will be 128 and 256. Here will be from 256 to 512. Right. So this is about this will be encoder 3, this will be encoder block 4, right? So we reach till here, okay? Now we need to convert it into a bottleneck feature, which is 1024. So let's say self dot bottleneck is equal to, it is also convolution block, nothing else, but we are just treating as a bottleneck block, right? So it will receive 512 and convert it into 1024. If you see here, it is 1024, right? So this is all about the encoder. We haven't written this max pooling block, which we will write in the forward method, okay? So now we need to create a decoder part, right? And decoder part contains up convolution basically, right? It also called as a convolution transpose, con transpose 2D, right? So let me write here first comment. It will be our encoder. Okay, so it will be our bottleneck. Let's say bottleneck features, okay? So now we need to create our decoder part, right? So if you see here in the diagram, so till now we reached here, okay? Till 1024 channels we reached. Now if you see, we need to apply one up convolution layer, right? So first one up convolution, then this convolution block will be there, right? So now let me write here self dot up convolution. So 4. So why I am writing here 4? So there are 4 encoder, right? So we are processing in the U shape, right? So 4. Now our up convolution also like 4, 3, 2, and 1, kind of that, right? So let me write up convolution 4 will be nn dot con transpose 2D, right? And in channel will be 1024 because it will receive the output of bottleneck layer, right, or bottleneck block, and then it convert into 512. If you see here, the number of channel will be 512, right, after up convolution. So when up convolution we will apply, we need to check what is the kernel size in that, right? So let's go to the architecture. If you go to the architecture, so if you see here, up convolution here, so If you see, every step in the expansive path consists of upsampling of the feature map followed by 2 cross 2 convolution, basically up convolution, right? So we need to use 2 cross 2 kernel size here. So let's write kernel size will be 2 and let's say stride will be 2. Okay, so this block will basically, this code will increase the size. So if you see here in the diagram, okay, so from 28 we will add 56 now. Okay, so this is our up convolution. Now we will need to create this block, this one, this blue arrow, right, which is containing two convolution block, one this one and this one, right? So if you see in encoder also we build this one, it is our con block, and now we apply this con block same, right? So now let's write self dot decoder. So we are using same notation 4321. Okay, so let's say nn dot, sorry, not nn, it is self dot con block and it will receive 1024 and need to convert into 512. Okay, now let's say self dot up convolution 3, it will be nn dot on transpose 2d. So if you don't get any idea here, just wait, we will, when we will implement the forward method, you will get better idea. Okay, so now this again we need to do up convolution. Now we will move to the 512 to 256. It is the reverse process of this, nothing else, right? If you see in the encoder, we move to 64 to 512, right? So now we will move to 512 to, if you see here, from 512 we are reaching a 64. At the end we will use 1 cross 1 convolution, which will convert 64 channels into 2 channels. Okay, so it will be same. Let me write kernel size is equal to 2, stride will be again 2, and then self dot decoder 3 will be self dot con block will receive 512 and convert into 256, right? Same self dot up convolution 2 is equal to nn dot on transpose 2d, it will receive 256, convert into 128, and then kernel size will be 2, stride will be 2. So this is the beauty of like UNet, you are using same kind of structure, right, in encoder and decoder, apart from this up convolution. First you are contracting and then you are expanding, right? So let's say self dot decoder 2 will be self dot con block, it will receive 128 and convert it into 64, right? Okay, 512 to 256, 256 to, sorry, it will be received 256, sorry, my bad, 256 and convert it into 128, right? Now final self dot up convolution 1 is equal to nn dot on transpose 2d, it will receive 128, convert it into 64, kernel size is equal to 2 and stride will be 2. Last decoder block, decoder 1 is equal to self dot con block, it will receive 128 and return 64 channels, right? Simple. So now we reach till here 64. Okay, so now we need output into a number of classes channels, right? So here there is a one object and one background, so we have 2 channels. So now final layer will be our fully connected layer of so not the fully connected layer, but it is like convolutional layer with 1 cross 1 kernel size, right? So let's say final layer will be nn dot on 2D, it will receive 64 and return out channels, right? So self, where we had mentioned here, right? Let me copy. No self will require, right? Out channels. Okay, and kernel size will be 1. So at last we are using 1x1 convolution. It is mentioned in the paper as well. Let me show you. Okay, if you go to the architecture, here is the line. At the final layer, 1x1 convolution is used to map 64 component features vector to desired number of classes, right? So here we written that line. Okay, so now we had, if I show you in the diagram, so till now we had built this part. Okay, the forward method is still pending when we write the forward, but we write all necessary blocks to build this part. Okay, now one thing is remaining, this one, copy and crop, because we need to pass this information here as well, right? So let's write this function basically which can crop this. So if you see, encoder output is always larger than the decoder output, right? So if you see here 280 cross 280, and when we need to concatenate it or pass this information here, the shape is 200 cross 200, right? Forget about the channel, because channel we can concatenate, but for that spatial dimension or height and width should be same, right? So now we need to convert this 280 into 200. So we will use center crop there, right? So let's write that function center crop. Okay, so let me write here, define crop. Okay, it will be self, it will receive the encoder output and it will receive the decoder output, right? Because we need to basically need the shape of it, right? So it will be the one batch size comma number of channels. Let's say here we will have batch size comma 256 comma 200 cross 200, right? Here we will receive a batch size into 128 comma 280 cross 280, right? So now we need to crop this 280 cross 280 into 200. So let's build that function. Okay, so let's say encoder size is equal to, this is not the actual encoder I would say, but it is the first block of encoder and output of it. Same for the second and third and everything, right? So when we are saying ANC and DEC in this function, this will be the output of this basically, nothing but else. Okay, so let's say encoder, let me write it encoder OP or decoder OP. Okay, at each block of encoder. So let's say encoder OP dot size. So it will return the size, and as we know, in the while we are doing training or testing, so first will be the batch size, second will be a number of channel. In the PyTorch we are using channel first format, right? So then we need to use from the two, which will be the height and then it will be a width, right? So it will basically return height comma width, right? So let's do same thing for the decoder, get decoder OP size as well, right? Let's say decoder encoder OP, decoder OP size. Okay, so now we have the height and width of the output of each convolution convo block. Okay, basically. So now we need to crop. So here if you see we have this 280. Now we need to centrally crop this to make 200 cross 200, right? So let me write the code for it. So let's calculate for delta H. Delta H will be a difference between encoder OP size of 0 minus decoder OP size of 0, right? So we are basically subtracting the height of encoder output minus decoder output, right? So same for the width, we will use 1 or 1, right? So now we get the difference between their height and width. So now we need to return encoder OP. Let's say first is the number of batch size as it is, number of channel as it is. Now we need to crop from the center part, right? So let me write the code. I will explain at the end. Okay, we can run this function separately so we can get better idea whether the shape is changing or not. Okay, so let's say delta H divided by 2. From this to we will write encoder OP size of 0 minus delta H divided by 2. From here we will, from the y-axis, let's say delta W divided by 2 encoder OP size of 1 minus delta W divided by 2. I'm using double slash for getting the integer output. Okay, so this will be our function. Let's run it separately and check whether the output shape is changing or not. Okay, or it is cropping properly or not. So let me remove the self as we are running it out of the class. So let's say a will be, let's build some random variable. Okay, so let's say it will be bit size 1, number of channel, let's say 128, and the let's take the output from here. Okay, let's say 280 cross 280, 280 cross 280. Now let's create the B, which can be a decoder output. So let's say it is 200, sorry, it is 200, and now let's apply this crop. Okay, so let's say R is equal to crop A comma B. Now if we see the shape of R, okay, so 128, 200, decoder OP. Let's see if we done any mistake. It should be 200. Sorry, it would be 128 cross 200 cross 200. Okay, so let's see if any mistake we had done. Okay, so it would be decoder size. Okay, here is the mistake. We need to use decoder OP size, right? Yep. So now if you see, we receive 1,128, 200 and 200. Now we had cropped this 280 from the center to get 200 or 200. Now we will concatenate it with the output of this, right? So let's change first here. There is one mistake, typo. Okay, so let me delete this. Okay, we get the idea, everything is fine. Now let's write the forward method. Okay, so if you have any doubt till now, you can you will get the clarified when we will build the forward method. Okay, so let's say self comma x is basically our input. Okay, so now let's start from the encoder part. So let's say encoder 1 will be self dot enc1 of x. Okay, so here we had seen after each con block, okay, this two, which is the convolution ReLU, right, we are applying the max pooling layer. So when we are building this constructor, right, I said like we will use the max pooling in the forward method. So let's do that. So now let's say encoder 2 will be self dot encoder 2, and here we need to pass max pooled output, right? So let's try nn dot max pool 2d, and we need to provide a kernel size will be 2, right? Okay, and then we will pass encoder 1. Oh, sorry, it would be like this. Okay, so what we are doing, we are receiving this encoder 1 output and we are passing it to the max pool, and the output of the max pool 2d will be provided to the encoder 2 block, right? Same, let's say enc3. We are writing the different name because we know we want it, right? When we are we need to pass here from encoder 2, we will pass from the decoder 2 as well, right? Okay, so now encoder 3 self dot encoder 3 nn dot max pool 2d kernel size is equal to 2, and we need to pass output of encoder 2, right? Same encoder 4 will be self dot enc4 and dot max pool 2d. Let's say kernel size is equal to 2 and we are passing encoder 3. So till now we created our encoder blocks, or you can say encoder network. Okay, so now bottleneck layer would be there. Let me write again here as well, right? So let's say it will be, sorry, it will be encoder. Now let's say bottleneck. Now it will be bottleneck will be self dot bottleneck. Will pass again max pool output, right? So let's say max pool 2d kernel size is equal to 2 and pass encoder 4. Okay, yeah, so till now we reached this bottleneck layer. Okay, 1024. So now we need to build decoder. So let me write decoder. Okay, so now let's say decoder 4 self dot up convolution 4, apply the bottleneck. Now decoder 4 will be self dot decoder 4. We need to concatenate the output of encoder 4 here. Okay, so let's write that. Let me write like this. Okay, it will be more readable. Let's say torch dot cat, and what we need to concatenate the output of this up convolution, basically decoder 4 output here, and this enc4, right? So let me write decoder 4, and before we cannot directly concatenate this, right? Because we know the shape of height and width is different. So first we need to crop it. So let's say self dot crop, and we will pass enc4 and dec4, right? The output of decoder block or output of encoder 4 block. Okay, and we need to concatenate it, at dimension 1. Okay, there is some bracket. Yep, this should be outside the bracket, right? Okay, so what we had done, if you see, we received this output center crop to match the dimension of this output and then concatenate with it, right? So this is about, okay, there is one, okay, this would be like this. Okay, and here there is some parenthesis. Okay, now it's correct, right? So we are concatenating the decoder 4 output, the centrally crop output of encoder 4, and concatenating them. Okay, now let's say decoder 3 will be self dot up convolution 4. Now we will pass decoder 4. Decoder 3 will be same thing we need to apply right here. Let me copy it. Decoder 3, here it will be decoder 3, this which one, this one, and here also 3 and 3, right? Same we will use for next step. So let's say it would be decoder 2, we need to up convolution this one, and now here we will decoder 2 output, encoder 2 and decoder 2. So basically we are building this part, right? Concatenation and then apply convolution block. So this is about the decoder 2. So let's say decoder 1 at the last self dot up convolution. Okay, so here it should be 3, it should be 2, and it should be 1. It will take decoder 2 output, decoder 1 will be, let me copy it again. Here is decoder 2, now decoder 1, 1, 1 and 1. Okay, so we reached till here. Now we need to apply final layer, right? So let's write the final layer. Now return self dot final layer, and it will receive the input as a decoder 1, right? So this is about the architecture of UNet. So let's run and check whether it is working or not. If there is any issue, we can fix it. Okay, so let me create a model, will be UNet, and we don't need to pass anything because in channel will be 1, out channel will be 2. We had already provided, right? Let's see. Okay, torch.rna has no attribute relu. Okay, where is the relu? I think in block, right? Okay, so it will be capital U, right? Again here also it should be a capital U. Let's run. Torch.rna has no attribute con transpose 2D. Okay, again there will be some spelling mistake, I think. Let's see. Con transpose, right? Oh, it should be capital, right? I think. Let's see again if there is any mistake. Okay, now it's work. So now let's use torch view to plot this graph so we can get the better idea. If torch view can plot the graph, our model is working perfect, right? So let me install pip install torch view. Let me write from torch view import draw graph, and let's call it draw graph model. Input size will be, let's say 1 comma 1 comma, what is the input? 572, right? 572 cross 572. Let's say expand nested true. Let's see it is working or not. Okay, I need to call some method, right? Draw graph or something. What was that? I think visual graph. Okay, let's see. Yes, visual graph. Take few seconds. Okay, now here we go. Okay, so if you see here, we started with 572, then we move 570, 568. If you see the diagram, it is same, right? 570, 568, right? And from 568, we extracted this output for the decoder part, right? So if you see here, we are concatenating this, right? Here, the output of the con transpose 2D and this one, and then we are passing it to our sequential block, which is our con block. The same thing we are using for each, right? From here we extract this output. From here also there are two paths. One will go for the decoder, which is this nothing but a skip connection, copy and crop, and this will be our continuation path, right? At the end we have the output 388 cross 388 with two channels, right? Which is same as shown in the paper. So here in the UNet paper, they are using a smaller size output, right? But there are many implementation which has the same, based on this UNet architecture basically, but has the same input and same size. There is nothing wrong in that architecture as well, right? But we are going to understand this paper. That's why I just implemented same as the paper. Okay. So this is about the UNet architecture and implemented using Python. If you have any doubt, you can write in the comment section. We can discuss there. And if you like my video, please press the like button and subscribe my channel. Thank you.